Alright, for the second version that we said we're going to go through, we're going to look at the practice problem from 09, parts A through E. Most of it very similar to what we've done before, but one part of it probably look a little bit new, so we want to go ahead and jump right into it. Now, if we're looking at part A just asks a simple question. Looking at the graph and looking at the information, what will be the independent variable? Now, the easy way to remember this is the independent variable, and I'm just going to put as I and V, is usually going to be what's plotted along the x-axis. So in this case, for part A, our independent variable is actually going to be the initial concentration of our thiosulfate ion. I'm going to shorten a few things, thiosulfate. Now, for the most part, that shouldn't be too much of a hassle. We should be able to pick that up fairly quickly. So let's go ahead and look into part B. Now, part B. Determine the order for the reaction with respect to the thiosulfate ion. In this case, we only have one reactant, so we'll go ahead and set it up just like we did before. I'm going to use our experiments 2/1, which will give me a rate of 0.30, divided by 0.020 equals K times the concentration of our A value, which is 0.075 raised to the M divided by K times concentration of 0.050 raised to the M. Of course, our K values here are going to cancel out. Now, when it comes to simplifying, we're going to be able to go 1.5 equals 1.5 raised to the M. So let's just know that our M value is going to be 1. So, with respect to our thiosulfate ion, our only reactant in this case is going to be first order. Now, that's part B. Now let's look into part C. Now, determine the value of the rate constant K for the reaction. Include units in your answer. So, just like we did before, I need to write my actual rate law expression. So, rate equals K, concentration of thiosulfate ion, 0.32 minus raised to the first power. So, plugging in my information, I'm going to use example 1, experiment 1. So, 0.020 equals K times 0.050 raised to the first power divided by 0.050 raised to the first power. I'm going to get K equals 0.40. Now, the last thing we need here is our units. Our units will be, since we started off, moles times liters, seconds divided by, so we're going to have to multiply by the reciprocal, liters times moles. Those are going to cancel. Those will cancel, so we'll just end up with 1 over seconds. Now, this takes us all the way up to part C in terms of the regular things that we've dealt with before. Now, this is where the change starts to come in. So I'm going to go ahead and start with a clean board so we can sort of work through this very quickly. this is where you're going to need that chart that I gave you. I told you want to memorize those formulas and how they are related. Because we know that this is a first order reaction, we now have to look at a couple other things. Now, it says in another trial, a student mixed 0.1 molar sodium thiosulfate with hydrochloric acid. So looking at a reaction, calculate the amount of time it would take for the concentration to drop to 0.020. So we know that the reaction or the formula we're going to use is natural log of concentration of A at time minus natural log concentration of A and its initial rate equals negative K times T. Now we have to plug in our values. So, I'm sorry. The rate that, or the concentration that we're trying to find out when we'll hit there will be the natural log of 0.020 minus natural log of our initial concentration, which it says is going to be 0.10, equals, we calculated our K value, negative 0.40 times time. So we're going to end up dividing both sides by negative 0.40. Now, moving down a little bit, we're going to end up with negative 3.91 plus 2.30 divided by negative 0.40 equals T. Our final value for T, once calculated, should come out to approximately 4.025. Seconds. So this is going to be this is the amount of time it will take for it to drop under regular conditions from 0.1 molar all the way to 0.020 molar. Now, the last step asks you to look at the graph that's given to you. And I want to make sure we have the space, so I'm going to go ahead and erase this stuff so we can make sure we get all of it in there. If we're looking at our original data, our original graph, you're going to notice that we're starting here. And this is our disappearance versus our concentration. Now, this being our 0.010. Actually, I want to just go ahead and redo this so it'll be large enough for everyone to see. There we go. Let's try this again. And beyond. And here, going with our original concentration. Now, our original diagram and graph would show our concentration starting at about 0.020 and increasing up this way. Hold on, I'm not sure exactly what just happened there, so let me go ahead and erase that, if I can. Okay, let's try this again. A line would go approximately this way as our data points would sort of back here, here, and so forth. If we were to drop the temperature, the main thing that we could expect to happen would be that we probably have the same slope, so the same rate of disappearance, but it would take a lot longer for it to happen. It would take a longer time because the reaction rate would slow down. This is what you're basically being asked to do for part E. Just analyze and see what would the initial effects be if we were to drop the temperature. By this point in the unit, you should be able to figure out and pick out what's going to happen at each step. Now, go ahead, take a look at this. Again, any questions you may have, write them down, and I'll see you in class tomorrow. Have a great day.